So welcome to the second session of today. And our first speaker is Professor Gautami Bhowmik from University of Lille. And she will be speaking on bounds on Siegel zeros. Please, Professor Bhowmik.
Okay, so thank you. Thank you for all this work. So I'm going to talk about bounds on Siegel zeros. It is quite possible that everyone in the audience knows everything about this question, but it is also possible that there are some people who I don't know who have come from somewhere because they don't know what to do on a Saturday and then they want to hear this talk. So I'll give you just spend a few minutes giving some details, okay, just to introduce the question. So what do I have? I have a Dirichlet character chi, which is modulus of some, so this is modulus some Q, and I consider the L function associated to it, which is the sum of chi of n by n power s and can be written as an Euler product. So in particular, you could have chi to be 1, and then you get the zeta function. Yeah. So of course you know all of that. So this is a very old question. This is in fact older than Riemann. It is 1837 by Dirichlet, who introduced this to study the class number and the infinitude of prime numbers in arithmetic progression. So where are the zeros? The zeros, the non-trivial ones, these are between 0 and 1. Yeah. So you have a 0 here, and you have a 1 here, and the zeros are, so that's where they are. Okay, and then what happens? Where do you expect them to be? Of course, you expect them to be here. Yeah. At so if you wrote out your if you wrote out your 0 as beta plus I times gamma, the chi need not be mentioned, then the beta should be equal to half according to the GRH, the generalized Riemann hypothesis. So, and then what do we know? We know that the real zeros, which are close to real s equal to 1, this doesn't happen very often, yeah? So so if you are close to this line here, then this doesn't happen very often. So that's what I say, that these are indeed rare. Yeah, they are rare, but they're real and they are rare. Okay, so so now suppose there is an exceptional 0. This exceptional 0 is called Siegel 0, and then some people have called it the Landau-Siegel 0, or sometimes an exceptional 0. This means that there is an exception to the generalized Riemann hypothesis. Okay, so if it does exist, then how does it behave? Then it is real. It comes once. It's unique, and it is one possible exception to the generalized Riemann hypothesis. So there could be other exceptions. So what do we know about this? So what we know about this, that if there is a 0, then all other zeros are going to be pushed away from the real axis. Yeah? This is the famous Doering-Heilbronn repulsion theory. Yeah. So what does it say exactly? It says that I'm giving it to you in the form of the way Linux stated it in 1944, because it could also be stated in the original form, but that's kind of slightly more complicated. And this is this is restatement of about 10 years later by Linnick, because during Heilbronn, I think it was in 1933 or 34, 30. So this is about 33, 34. And then this is about 10 years later that Linnick stated this. And what does it say? That if there is an exceptional zero, beta, we call it beta, and with this property that 1 minus, that 1 minus beta is less than epsilon times epsilon divided by log q, and epsilon is rather small, then all other zeros are going to behave for a given L function with a modulus q, such that 1 minus beta, 1 minus sigma is going to be bigger than some constant times log 1 by epsilon divided by log q, 2 plus absolute value of t. And this c that you see here, this c, this is an absolute positive constant. Yeah, so Linnick used this to find the size of the least prime in an arithmetic progression. So, so what's nice about the way this result is stated is that we gain by a factor of this, we gain by this factor, log 1 by epsilon. Okay. And there is this result was strengthened by Bombieri, who showed that this was much later, 1987, and Bombieri showed that I take some t, which is greater than or equal to 2, and beta is an exceptional zero for sigma greater than some constant c by log t. Little t is bounded by the big T. Then there exist constants C1 and C2, such that the same 1 minus delta that 1 minus sigma that you see here, this can be written as C1 times two constants C1 and C2 log C2, 1 minus beta log T, and the whole thing by log T.
Excuse me, so can you just move your slide slightly to the left? So we are getting a partial, yeah.
Okay.
Yeah, that's it.
Is it better?
Yeah, so okay, it has moved a little too much to the left. So slightly, yeah, that's okay. That's perfect. Perfect.
Okay. So this is Bombieri's result in 1987. And if you wanted, you could have stated this as a density estimate. And this is, as a density estimate, it would look like this. So you could have written it like this. N alpha qt is less than 1 minus beta log q 1 plus log t by log q qt times big O of 1 minus alpha. Okay, what are all these things? So, and what is this this n? It is now the number of zeros which are counted with this n, this number of zeros counted with multiplicity. And for any L function of modulus q, this alpha alpha is a bound for sigma. So alpha is between, so sigma is between alpha and 1, and little t is between 0 and t. Okay. So this is a density estimate. Yeah. And this is, I'm writing it the way, what the nice result that you will get if you use Bombieri's expression. Okay. So now here's a result everybody knows. This is Siegel's 1935 result. It says that if there is an exceptional zero, which is associated to a primitive character chi, which is conductor Q, and if you choose your epsilon positive, then you can find C epsilon, which is greater than a C epsilon, which is positive, such that 1 minus beta is greater than C epsilon upon Q to the power epsilon. Now, what's good about this result? Of course, it gives a bound, but what's not good about this result is that this result is not effective. Okay, so this result is ineffective, and the fact that it's ineffective, it's ineffective every time epsilon is less than half. It makes that it says that we cannot use it for many applications. However, nothing much has happened. Siegel, you see, this is 1935, which was very long ago, and seriously, unconditionally, this result stays as it is. So only possibilities are to sort of go around the story. You see, you go around and you try to see if you can put some conditions which will make it better. If you can study, for example, the zeros by some other method, for example, by looking at the value at s equal to 1, etc. Then it's these are some ways somehow to go around the problem, because essentially the theorem as it stands has not been yet improved. Yeah. So there is a version by Tatuzawa for the effect. There is an effective version of Tatuzawa in 1951. But it's a partial result, yeah. So sort of effective, yeah. But yeah, so that's why I put some brackets around it, yeah. So what do we know for these zeros of LS chi and their values at 1? This is known since forever. And what we know is that if we have, so these are closely related. So for example, if I have L1 chi is less than or equal to, L1 chi is less than or equal to some constant, positive constant times small positive constant times divided by log of Q, then 1 minus beta is less than or equal to 1 by log Q. Yeah. So that's something that's known. And using using what Friedlander and Ivanic in a somewhat recent paper, they say that they call the Heilbronn, they call it the ultimate Doering-Heilbronn property. Using that, they can show that if 1 minus beta is less than, that is in the other sense, yeah. If 1 minus beta is small, then Ly chi is small, yeah. They proved this using the DH, yeah. A certain form of this DH. There are many forms of this. So Yeah, there are other applications of this L1 chi. One example that probably everybody has seen, that is that if you have L1 chi to be, if you have the class number formula for this one, L1 chi equal to pi HQ by square root of minus Q, then you get the prime number theorem in arithmetic progression, and you get an elementary lower bound, yeah? And you get an elementary lower bound, L1 chi, which is bounded by 1 by Q to the power half. However, the good effective lower bounds are very difficult to get, yeah? You are looking for two things, it's good and it's effective. So what do? You can't quite just sit down and feel very bad about it. And so this is elementary, yeah. There are some improvements, but usually under some conditions. So I want to talk about some of these conditional bounds. The first one is really old, 1928, it's a little bit. And this says that if you assume the generalized Riemann hypothesis, then L1 chi is bounded by, on both sides, by 1 by log Q and log Q. And this can be, you can actually, Littlewood actually gave the constants here, yeah? He gave these constants here. So this is here, sorry. That's bad. Yeah, so you can get some constants here, half of little o of 1, and here you can get 2 plus little o of 1 e to the power gamma. Gamma is Euler's constant, but only the implied constants can be, these implied constants are therefore effective, but only these can be improved. This bound is optimal because there's a result by, there's omega result by Chawla. This is 1949 and says that this cannot, which says that you cannot really do very much better. So under GRH, this is about what you can expect. There are improvements. Some people continue to improve things under some assumptions, etc., especially trying to see if they can do anything better with the constants. And so you can't do much with the GRH. So you can do what you can do. So let's see if you weaken the GRH, what happens. So that's what. So here is a modified GRH. It says that if there are zeros of LS chi, then they are either on the critical line or on the real axis. Okay, this is the modified generalized Riemann hypothesis. I don't know who first thought about it. I know that this exists in a paper of Sarnak and Zarascu, and they show that if we can assume this, if we assume that all Dirichlet LS chi satisfy the modified GRH, then L1 chi is bounded by some positive epsilon, for any positive epsilon, by C power epsilon log absolute value of epsilon to the power epsilon. Yeah. So this result is not effective. Yeah, this is not effective. But if you add some more conditions, it can be made effective. They show it in the same paper that if you add some further conditions, it can get better. Yeah. So this is one way of, you do something, you change your GRH and you can get some results. And then Friedlander and Ivanic, they say, they allow some exceptions. They say that the GRH is true, which it probably is, and except for only one beta, and for that beta, they give a condition. They say this beta is greater than 3/4. So I call it GRHE with exception. And then they show that if this is the case, if we assume this GRHE, then 1 minus beta is bounded by, no, if I assume GRHE and if 1 minus beta is less than 1 by log Q, in that case, L1 chi can be bounded by 1 minus beta log Q square. Yeah. So here, and on the other hand, by 1 minus beta. But the conditions are assumed. Yeah, certain conditions are assumed. Yeah. So now I want to give you some other exception. Conditional cases. So this goes via the Goldbach problem. The Goldbach problem, as you all know, it's finding little g of n and writing it as P1 plus P2 for 2 primes whose sum is n, and of course you see whether n is odd or even, and what is an old result in this direction? It is a conjecture of Hardy and Littlewood of 1923, old, so 100 years old, yeah. So it says that g of n can be very nicely approximated by a singular series, which is given as the product over all primes that do not divide n, yeah. Okay, 1 minus 1 by p minus 1 square, n by log square n, and you have an n by phi n, and this should be a good approximation. This is expected, yeah. So and what is this? This can be written as, so you could also write this as, I'm just stating it because of a certain reason which you would see. So this is equal to 2 times C2. So this is the twin prime, the constant of involved in the twin prime problem, and some product here, and the same thing here. And this C2 is about 0.66. Yeah. So this is approximately 0.66. Yeah. And here, and so there are some conjectures. For example, Andrew Granville has a conjecture that the GRH is equivalent to an asymptotic form of the average Goldbach formulation for arithmetic progressions. And this conjecture has not been completely worked out yet. So, however, what is known, one of the things that is known in this direction is a result assuming a weak Hardy-Littlewood conjecture, weakening the Hardy-Littlewood conjecture. This says that there is some positive constant, yeah, delta, where such that g of n is this representation of n as sum of 2 primes, Goldbach representation. If this is greater than delta n by log square n for every integer n greater than 2, then phi proved in 2016, then if we assume this, and if there is an exceptional 0 beta for a chi which is which has an underlying prime modulus Q congruent to 3 mod 4. In that case, you can improve on Siegel's bound. You can get 1 minus beta is greater than or equal to C by log square Q. So what phi does is he gets a lower bound. He gets a lower bound using the weak Hardy-Littlewood conjecture, and he gets an upper bound using the prime number theorem in arithmetic progression. Okay. So what I want to say is that we can somehow improve on this result of phi's by assuming a condition which is weaker than phi's. So here is phi. It says there exists a positive constant, delta, such that g of n is larger than that. And we can make this weaker, and we can include some other conditions more than this q congruent to 3 mod 4. Yeah. So as a special case, so this one, yeah. So as a special case, it should give phi's result. Yeah. Okay. So it's not a wonderful result. Yeah. So it's a small improvement I mean, it's not even really an improvement on Siegel because it's conditional. Yeah. So what is our, because it's a result with Karin Halupczok of Düsseldorf. And we make a conjecture that if x is large, yeah, we make a conjecture that x is large. How large? We will see. And q is greater than x by 4. Then we admit some exceptions. This is similar to what I have shown you before, that with you take GRH and then you say that it's true except for some exceptions. So I need this to assume that there are exceptions at most x by 8q times. Then we have g of n is greater than n log square n. So for a given interval, for n which is between x by 2 and x. Okay, it might look artificial, it probably is. And but these are things we needed to be able to improve on the proof. So we assume that this conjecture is true. We assume this, yeah, Gn greater than n log square n under certain conditions. Yeah, and we need a further condition that chi minus 1 is less, chi minus 1 is equal to minus 1. Okay. And assume now that there is a beta. There is an exceptional 0. And then we can show that if this is the case, then 1 minus beta is greater than c by log square q. There exists some such c, which is a positive constant. Now, so it is a conditional improvement on the Siegel, on Siegel's theorem. So I can give you some an idea of how the proof goes. So this proof is like it's we'll get a lower bound and we'll get an upper bound, and some nice things will happen in this. So it uses the circle method, yeah. So the proof uses a simplified circle method. So it is a simplified circle method, which uses only one modulus, yeah, and we use the prime number theorem in arithmetic progression, and then we compare. It is not very, very different from phi's proof. It is, however, it is done little bit. It's pushed to where we could push it. Yeah. So remember that q in our condition, we had that q was less than x by 4. So the q being less than equal to x by 4 is still used. And then we have S, we want to find this sum. We write it as a sum for all k was an exponential sum kp by q square, and the prime is between 2 and x. Okay, and so to prove this, let's call this S1. I write my prime as P1 plus P2. Okay, P I write it as P1 plus P2. And to be able to get some nice cancellations. Okay, so this E now becomes, instead of having K of P, I have it as E K P1 plus P2 exponential of this by Q. Okay, and Q, as you remember, is less than or equal to Q by 4. So with the conditions that I have, I can get the sum of 1 for P1 and P2 between 2 and x. This will be greater than or equal to delta x by log square x. Okay. So, and then you have another sum. So then you try to get an explicit expansion. So here I have used the weakened Hardy-Littlewood conjecture with exceptions. Otherwise you cannot get this. Otherwise you cannot get this in our proof. I don't say that otherwise you cannot get it. I don't know. Okay. Then we get an explicit expansion. What do? We take two cases where Q is divisible by a prime and Q is not divisible by a prime. Okay. So if Q is divisible by a prime, then we not divisible by a prime, then we use the prime number theorem in arithmetic progression. Yeah. So then okay, what we can get is S1. This is equal to some m plus, here is my Ramanujan sum. Okay, Euler phi, okay, plus big O of Qx for some constant C tilde square root of log x. So what is m? M is equal to, and here comes the Gauss sums. Okay. And you get an integral to x. Okay. So this is a Gauss sum, and this is the, so now this you cannot see. So so here is Ramanujan sum, okay, and here is a Gauss sum, okay. So probably I don't have to, and then for the Ramanujan sum, I can bound it, and for the and the Gauss sum, I can use some estimates on this Gauss sum. Yeah. So if you do this, some nice things actually happen, and there are cancellations that are possible. Yeah. Nice cancellations take place. Yeah. And the Ramanujan sums disappear. Okay, which is quite nice. Yeah. So cancellations take place. So Ramanujan sums disappear. So actually, probably you don't need this. Probably you can do it directly without the Gauss sums. But well, it will not give anything new, but maybe another way, a simpler way to do it. I don't know. Yeah. So once you have done this, then you split the sum S for k equal to Q and k less than or equal to Q. And then you get S is equal to, for k equal to Q, you get this form. For k equal to Q, you get x squared by log square x. And then you get some more terms. Yeah. And what is this error like? And the error term is like, you can expect something like x squared log cube x. So it's a big O of, if you work this out, q squared by 5q squared, and so on. Yeah. So you have to choose now. So now you choose your x carefully. You choose it. So one part of this choice comes from your assumption, the WHLE, and another is to make sure that all the results that we are using are not none of them are contradicted. Yeah. So you use that. So so when you now remember that we had this condition that chi minus 1 was equal to -1. Remember, it's not very nice as a condition, but we need it. Yeah, I mean, we need it for our proof. So and then you get this error, which I just showed you. Okay, and so that's what I mean when I say that choose x appropriately. Means neither too big nor too small. Okay, so to keep everything going. Okay, and then as I said, you compare them, and you get the result. Okay, and I want to say that these constants all of these are effective. Why are they effective? Because what we used is the prime number theorem for arithmetic progressions. So if you use the prime number theorem for arithmetic progression, then you get your constants from there. Yeah, just as the delta that we got here, this delta for our proof, it's enough to have it just small. But I think you can go up to 2 times C. So C being 0.66, this will be 1.32. Probably you can go up to 1.32. And then you can actually effectively work out all the constants. So even if this result is conditional, at least you can get the condition, the constants effectively. Okay. So now what has happened is from phi's case, we have moved to including some composite moduli. Phi had only prime moduli, and phi also had the case. So this is a corollary of our result. It says that if you assume this conjecture, the weak and Hardy-Littlewood conjecture with exceptions, and if Q is sufficiently large with some conditions, which comes from your chi, then there is a beta such that 1 minus beta is large. Yeah. And so which case is phi's? Phi's is the case that Q is congruent to phi's Q is equal to P, and it's congruent to 3 mod 4. Yeah, you see that here. This is here. So this is phi. Yeah. So it follows from that. It also from this result, again, these are conditional results, as I said. So if we assume the weak and Hardy-Littlewood conjecture, if we assume an exception, so many assumptions are there. So you use Hardy-Littlewood conjecture weakened form. You use the form chi minus 1 is minus 1. And if you take the conditions of Iwaniec and Friedlander and Iwaniec, then that the GRH holds except for a possible beta, which is at least 3/4, no more than 3/4. In that case, you will be able to show that L1 chi is greater than 1 minus beta, and it's greater than 1 by log square q, which is a slight improvement on the Iwaniec Friedlander result, but includes more conditions. Yeah. So having said all this, you are probably somehow frustrated because these results are, as you see, everything I've given in yellow, it has lots of assumptions. Hardy-Littlewood, the weakened Hardy-Littlewood, chi minus 1 equal to minus 1, etc. So is there any hope? So, okay, I should have a new page here. So, yeah, this is the time to say that I'd like to thank all of you. That is Shanoli, Anirban, Purushottam, and Shukumar Da, who is also Shukumar Das. So, and I hope that we will meet for Balu's 80th birthday. If by then maybe the situation will be better. So, so now let me say if there is any hope. So, are there any hopes? Then, so the conditions. So, so what are the hopes? Hopes are that can we find an equivalent of the weakened Hardy-Littlewood conjecture? Does it exist anywhere? I don't know whether it exists anywhere. Some kind of, and if there is an equivalence, or if something implies the weakened Hardy-Littlewood conjecture, then maybe we can say something more. Something else that I would that is irritating is this: chi minus 1 is equal to minus 1, right? This chi minus 1 is equal to minus 1. Can we forget this? So here I think that maybe if we take the g of n, if we take the g of n to be less than or equal to 2 minus delta, instead of having delta times n and log square n, then maybe we get a lower bound, which is delta, and an upper bound, which is 2 minus delta. Yeah. So so this is actually morally quite close to a sieve parity problem, and this might be doable. In that case, probably chi minus 1, some more chi minus properties of chi, some more chi can be included in the proof. And yeah, perhaps I should stop now. Yeah. So I wish Balu a very long continuation and many proofs and everything good that should happen to you and to people around you. Okay.
So if there are any questions, then you can unmute and ask. So if there are no questions, we thank the speaker. You can unmute and clap. That's what we have been doing.